In this short presentation, we want to touch on the basics of two of the most efficient, and at the same time, two of the cheapest exploration and targeting techniques. We will be talking about lineament analysis and physical modeling, both of which can be conducted either separately or in combination. This presentation is not aimed at the professional geologists, for whom we will be releasing a short series of online videos in the near future. It is mainly addressed to investors and managers in the mining industry. In other words, to the fairly broad spectrum of people with interests in the mining stock market. Let us come straight to the point. Natural lineament can be generally defined as linear feature on the Earth's surface visible on the map. Lineaments are the result of heterogeneity, anomaly, of physical, chemical, biological properties underneath, faults and fractures in the first place. These anomalies, more precisely their projections, become exposed by erosion and can be seen by a naked eye or detected by special surveys on the surface. Accordingly, one may speak of topographic, photo, satellite, geological, and geophysical lineaments, etc. These linear features are essentially nothing else but the surface reflection, projection, of either a geological body, such as a dike or a layer, or of a plane of anomalous physical property, such as fault rupture, zone of mechanical weakness or hardness, of high or low permeability, etc. Hence, by studying lineaments, we indirectly study the surface pattern of the uppermost crust's physical property, and mainly the distribution of fractures and faults projections on the Earth's surface. Let me use another example to explain the nature of lineaments. For instance, if they form some hidden linear or invisible flaws on the wall or floor, then with time, they will be growing into more and more noticeable features due to the wet-dry cycles. Eventually, such wall or floor lineaments will surface. Most importantly, following these lineaments towards the inside of the wall or under the floor, we can get to the source of the leaking. There is almost a complete analogy here with the uppermost section of the Earth's crust. Small movements along the fault and the fluid flow with time, and eventually will produce a zone of higher fracture density and alteration above. By studying the lineaments on the surface, we can outline this zone as anomalous and start looking for the underground deep structure. This structure can potentially lead us to the discovery of the ore body. Now, how to draw lineaments? It is pretty straightforward. Look at this satellite image. One can see the obvious differences in the color, texture, brightness, and contrast in the different parts of it. We humans have an intrinsic ability to recognize common geometrical shapes, like lines, circles, etc. Without thinking, we draw the lines highlighted in this slide, and we can go on and on. There is no magic in drawing the lineaments, just attention and patience. In this slide, you can see a geological map. Again, one can immediately see some linear features on the map. These are either sections of the geological boundaries or faults. In other cases, they may represent dikes, shear zones, or linear alteration zones, etc. All these linear features are regarded as geological lineaments. Now, here is a magnetic field map. Colors correspond to different values of magnetic susceptibility. Again, the change in color allows us to draw linear features, and they mark abrupt change in physical property. In the center, you can also see structures of circular shape. They are called circular lineaments. In most cases, they correspond to projections of intrusive or extrusive bodies, and sometimes impact structures. Straight lineaments, projections of planes, can be divided into different scale groups according to their length and corresponding to their depth. For instance, group of tertiary lineaments, small and relatively shallow. Group of secondary lineaments, medium length and depth. Group of main lineaments, long and deep. Such division is project area dependent. For example, for the small area, say 3 by 3 kilometers, the lineament 1.5 kilometers long may be grouped as the main one. But for the project with an area of 50 by 50 kilometers, the same lineament will be taken as the tertiary lineament. So, let us revise the definitions again. Main lineaments can be clearly traced through at least 1/3 of a map, or if shorter, are of considerable width. That may be represented as a series of closely placed parallel lineaments. Secondary lineaments can be seen as straight lines, due to changes in surface pattern or color nuances, extended through at least 1/20th of the area in the image. Tertiary lineaments can be seen as straight lines due to changes in surface pattern or color nuances, extended through at least 1/100th to 1/20th of the study area in the image. Circular lineaments in some cases may be divided into 2-3 scale groups by their diameter. The lineaments may also be weighted. Weighing is arbitrary and reflects the researcher's conception of the lineament's nature, origin, and importance. The fractures or fault shape must be similar to a square or disc. So, the lineament, say 200 meters long, may cut into the rock down to approximately 200 meters, and the main lineament 6 kilometers long, accordingly to 6 kilometers down. Such a conception may be an oversimplification, yet the tendency of the longer and wider lineaments to penetrate deeper than the shorter ones is a well-established geological fact. Apparently, an amount of fluid flowing through the main lineament is larger with comparison to the tertiary one, and the mineralization is more likely to occur in the vicinity of the main lineament. Therefore, it makes sense to assign the importance of value to the main lineament heavier than the secondary and much higher than the tertiary. In our processing, we use the following weighting coefficients: tertiary, 1, secondary, 3, main, 10. Circular lineaments are also very important, since they often reflect the existence of the intrusive body nearby. Therefore, we weigh them as 10. Processing of the lineaments goes through the following stages. 1. Calculating the number of different lineaments in the windows of chosen size. 2. Producing the maps of lineament densities, separately for different scale groups and combined. 3. Calculating the number of intersections of different lineaments in the windows of chosen size. 4. Producing the maps of lineament intersection densities, separately for different scale groups and combined. Let us not forget that the lineaments are nothing else than the projections of the faults onto the Earth's surface. Consider the situation where we have two faults, fault plane 1 and fault plane 2. Each of them with its specific fluid flow rate. These faults intersect each other. Then, along their intersection, shown as the tube in the slide, the fluid flow will be at least 2 times greater in magnitude than along the individual planes. In fact, because of the so-called resonance effect, or self-increasing effect, the fluid flow along this zone may be much higher than 2 times. Considering the intensity of the fluid flow is an important factor in mineralization, it becomes clear that the spatial distribution and density of the lineament intersections is equally important. Okay, the main outcome of the lineament analysis is a series of tables which gives us the number of different lineaments and their intersections for the windows of the chosen size. Example, tertiary and tertiary. Tertiary and secondary, secondary and main, and so on. The program that does the calculation was designed specifically for my technique, and it is incorporated into the ArcView program. These tables are then processed either in the ArcMap or in Surfer, or in both, which results in the series of maps of lineament and their intersection densities. Basically, the maximums on the maps correspond in space to the most promising areas for further exploration efforts. They represent preliminary exploration targets. In addition, The lineaments are processed in terms of their preferable orientations. Rose diagrams of different types are built, from the standpoint of fractal dimensions and in some other ways. I will address these additional methods in the detailed online course later. Let us stress the main idea of the structural lineaments analysis one more time. The resulted maps are contour maps of lineaments or lineaments intersections densities. The maximums on such maps represent the areas with the higher lineament population, and therefore with the highest permeability for any fluid flow passing through the system. Contour maps of lineaments densities for different lineaments and different averaging window sizes often repeatedly show the same, or spatially close, areas with higher densities. These zones are taken as the most favorable for mineralization, and may be recommended as the first target zones for future exploration activities. Now, we are done with lineaments. We have all our maps. We know the frame of the main lineament structures, but how do they interact? Theoretical consideration, as well as experimental results and geological practice, indicate that only a few, among many faults and their intersections, play a controlling role in deposit location, whereas others serve either as pathways for fluid or don't affect the geological system at all. This phenomenon becomes clear from the following simple experiment, which everyone can reproduce at leisure time. Let us take a rubber eraser and make several cuts on one of its facets. Then, press the eraser from two sides horizontally. You will immediately see that the openings form along some cuts, which are parallel or close to parallel to the direction of compression, whereas other cuts do not manifest themselves at all. Now, let us try to press this eraser in different directions, bend it and twist it around. We will find a number of deformational patterns, yet the initial system of cuts stays the same. This experiment gives maybe a bit oversimplified, yet a good analogy of faults interaction in nature. So, how can we better understand the interaction of the lineaments? The answer is physical modeling, also known as analogue modeling. Analogue modeling is a simplification of nature. Using this method, structures formed due to the deformation of rocks can be modeled and investigated. Physical modeling deals with simulation of real geotectonic processes by using analog materials instead of rocks, and substituting natural tectonic stresses, temperatures, and pressures by specifically selected laboratory conditions. Our lack of knowledge about real rocks is one of the major limitations to any kind of modeling or deformation. However, unlike their counterparts in nature, the initial, underformed stages of analog models can be documented and can be easily compared with their later deformed stages. This comparison is essential to gain an understanding of the evolution of the resulting structures. Analog modeling is a relatively simple and inexpensive technique which can be very valuable as long as its limitations are well understood. Basically, tectonic deformation, as any mechanical deformation, consists of three consecutive stages: elastic or reversible stage, plastic stage, and rupture, being both permanent and irreversible. To model elastic deformation, we use elastic material, gelatin most often. To model plastic and rupture deformation, we use clay pastes. In this slide, you can see a few of such experiments in motion, just to get a feel of the process. Obviously, any particular lineament project demands its own design of the experiments. Geological practice and theory tell us that in general, during the deformation, mineralized fluids move from zone of high compressive stresses into zones of openings, ruptures, fractures, and faults, where they precipitate and form ore bodies. So, we want to prepare a model with the main structures cut, and then deform the model in all the possible directions. Then, Register and record the resulted structures. Usually, we record the experiments with a digital camera. Then, processing the results, we outline the ruptures and newly formed fracture zones in all the experiments. After that, we overlay all the experiments on each other and outline the zones where the ruptures and openings happen in most of the experiments. Such zones, from the modeling standpoint, may be taken as the potential traps for the mineralized fluid, and therefore the most favorable for the future exploration activities. The previous slide showed the plastic deformation and rupture experiments. In this slide, you can see the illustration of the same principle applied to the elastic deformation. The method is based on the property of birefringence, which is exhibited by certain transparent materials. Birefringence is a property by virtue of which a ray of light passing through a birefringent material experiences two refractive indices. Photoelastic materials exhibit the property of birefringence only on the application of stress, and the magnitude of the refractive indices at each point in the material is directly related to the state of stress at that point. To analyze the level of the stress, the Michel-Levy interference color chart is used. We use gelatin as the optically active and most suitable material for this purpose. The gelatin sample is placed between two polarizing plates, perpendicular to each other, and put on the light table. The deformation is being applied to the sample, and the interference image is photographed. When all the experiments are done, we outline the areas of high, medium, and low stress deformations for each of the experiments. Overlaying these patterns onto each other, we usually find that in the model, there exists such zones where the deformation was high in more than a half of the cases in all of the experiments. These repeating zones of high fracturing and openings, or traps, in the plastic rupture series and zones of low stress, or openings, in elastic series, both represent the most favorable places for the formation of ore deposits. As it was said in the beginning of the presentation, lineaments analysis and physical modeling can be done separately. Each of these independent methods produce valuable results and lead to the target generation. Yet, the best results are obtained when we combine these techniques and the results they produce. What we do is overlay the exploration target maps built by structural lineament analysis and by analog modeling. Then, we outline the areas where the targets of both maps happen to be either in spatial coincidence or spatially close to each other. These areas represent the first-order exploration targets. They should be focused on in the field first. The data obtained during the structural analysis and modeling can also be processed by the original statistical method of Mr. Valls to determine the range correlation coefficient, or RCC, that best characterizes the mineralized zone. RCC is in some ways very similar to factor analysis. They both identify those elements that explain the majority of the variability of the data, but the RCC adds in a ponderation component since it gives more importance to such elements that are more involved in the mineralization process. In practice, RCC statistics produces independent exploration target maps, which can be compared and analyzed together with structural analysis target maps and modeling target maps. In many cases, the RCC method allows to lessen the number of exploration target areas, selectively focusing on the strongest targets. What will you have in the delivery package? From the structural lineaments analysis, you will receive the following results. Maps of all lineaments of the properties: tertiary, smallest; secondary, medium; main, regional scale; and circular, which most often reflect intrusive bodies underneath. Rose diagrams maps for the properties and surroundings, and also maps of the spatial distribution of the preferred orientations of lineaments, fractures, and faults. Contour maps of various lineament densities and their intersections in various combinations. Overlays of the lineament maps above on the geology, geophysics, geochemistry, or anything else you have. Often it allows revealing a new pattern in the relations between mineralization and structure, and consequently, It shows where to explore further for the previously unknown mineralization zones. Exploration target maps based on the lineaments and additional info you already have for individual properties and surroundings. In other words, you will have few new layers of data and interpretation based on all data you have, and our results from the structural analysis. You will have new exploration target maps, and of course, the report will wrap up all the results. Analog modeling. As a product to deliver, you would have a report on the modeling with experiments, pictures, interpretation, and exploration target maps based on the elastic and plastic deformation patterns. Again, in other words, you will have a few new layers of data and interpretation based on all data you have and on our results from structural analysis. That is new exploration target maps for the properties. Structural lineaments analysis can be done separately, without subsequent physical modeling. Yet the combination of two would be recommended, since it strongly increases the reliability of the interpretation. RCC statistical application is also very recommended. It could be done in pair with structural analysis results alone, with additional layers of database, table, data, and with all the results available for processing. Now that we have come to the end of the presentation, we would like to summarize the reasons you would want to try to apply the remote exploration technique to your properties. The main reason: it works, but also, number 1, solid scientific background and proven success. The ideas and assumptions in use are well grounded, with many recent successful projects. Number 2, state-of-the-art computer processing and GIS environment. The client is given exact coordinates of the targets, as well as GIS formatted layers of information that he can use later. Number 3, the method is synthetic. It incorporates all the available geophysical, satellite, topo, geochemical, geological, and any additional data. Number 4, the low cost. All the methods use data available for free or cheap online that dramatically downsizes the cost of the exercise. Number 5, the method is fast. In most cases, the process takes about 2 months' time from the beginning to the final report, which includes all the processed information, databases, graphical data, and interpretation. Thank you for your attention. We are looking forward to hearing from you. To talk about the details of your project, we will be happy to arrange a Skype conference call or any other way of video or audio discussion. Please contact us using either the email address or phone number provided, and we will start the conversation from there.